We use batteries every day in our lives, in mobile phones, laptops, cars, and so on. Battery technology itself has been around for a long time, but the energy transition is putting huge pressures on developing better batteries, more efficient batteries, and just building more of them. But what metals and elements actually go into making a battery?
Most low-carbon energy solutions require batteries. We all know that electric vehicles run on batteries, but in addition, low-carbon energy production and transport itself requires ways to store energy and to balance and manage power feed both into and out of the grid. Solar and wind farms and their transformer stations, the electricity grid, electric vehicle charging stations, and the electric vehicles themselves, of course, all of these are dependent on energy storage and power output management.
And this, in most cases, means batteries.
A battery is a device that stores chemical energy and converts it into electrical energy. The chemical reactions in a battery produce a flow of electrons from one electrode to another, and it is this flow of electrons that provides the electric current. In its original and very basic form, a battery simply consisted of a stack of metal discs separated with a layer of salt. The chemical reaction in this stack produces the flow of electrons from the anode in one end of the stack to the cathode in the other end of the stack. The materials and configurations used in a battery have evolved, as different materials have different electrochemical properties, and so they produce different results when you put them together in the battery cell. The differences in the chemical reactions affect how the battery works and how much energy it can store.
So there's a huge range of different battery types, all used for different purposes.
Many batteries used in our everyday tools, cars and gadgets are either lead-acid batteries, alkaline batteries that use zinc, manganese oxide and potassium hydroxide, or nickel metal hybrid batteries that in addition to nickel contain cobalt, manganese or aluminium, and also many elements such as lanthanum, cerium, praseodymium or neodymium. But most batteries currently used in the energy transition technologies, as well as in our mobile phones, laptops and in electric vehicles, are high-performance lithium-ion batteries, although electric vehicles also often use a conventional lead-acid battery as an auxiliary lower voltage power source.
So lithium-ion batteries have higher energy densities than lead and nickel-based batteries, meaning that basically they can store more energy for less material. So lithium batteries are lighter, whilst at the same time basically being more powerful.
There are many types of lithium-ion batteries, the main difference between them being their cathode chemistry, but they are all based in the same principle of the anode and cathode sitting in an electrolyte solution. The electrolyte is usually a solution of lithium salts in a mixture of solvents such as dimethyl carbonate. The cathode is made of lithium combined with other metals to improve the stability and performance of the battery. The other metals are usually nickel, iron in the form of iron phosphate, manganese, and cobalt, the exact combination depending on the desired performance and cost of the battery. The anode is usually graphite. The problem with graphite, however, is that over time, graphite eventually weakens and breaks apart as the lithium ions get repeatedly inserted into the graphite structure. Researchers are working on developing options to instead use graphene, which is much stronger in this respect, and is essentially just graphite split into very thin sheets, only a single atom thick. In addition, other metals such as tin and copper are needed for the electric circuits and soldering the electrical connections in a battery.
There are many new battery types in development, and the aim of this is of course to reduce the cost and the amount of materials needed for these batteries, whilst at the same time improving the performance of the battery, such as the energy capacity, energy density and charging speed.
For example, lithium-sulfur or sodium batteries would be cheaper alternatives to lithium-ion options, as both sulfur and sodium are cheap and abundant. Another example is a solid-state battery, where a battery's liquid electrolyte is replaced with a solid material such as a plastic polymer or inorganic powder. This technology would in theory make it possible to increase energy density and stability while making the battery cheaper and less likely to self-ignite. Problems with battery types under development arise from things like stability, production cost, and durability.
But whichever battery types we end up using in the future, some things are certain. First of all, they will all require resources, metals and elements. And secondly, as the energy transition gathers pace, we will need to build more batteries, meaning that we will need more metals and elements.